We all have one.
Yes.
Now the easy part. Okay.
Russell.
Thank you for still being here. We got a lot of good questions, and I had a chance to look through them, and have chosen some. And as usual, I'd planned to ask the panel some questions myself, but because it went on a little long, I'm going to go to your questions first, and we'll see if we have any time afterwards where I can provoke people. So we're going to start with sort of some basic stuff and move out to the edges of reality. And I think I'm going to try something a little new here, and I hope you don't mind if you put your name on here. I'm going to mention your name and ask you to stand up, okay? And I'll try and direct the question to different people. Okay, Nadine, are you out here, Nadine? Nadine? Yay! There we go. Nadine's excited. Okay, this is a common question, and probably a lot of people have it, so I think it's important that you asked it. If the universe is expanding, where is it expanding from? What is its center? How do you know it's not just moving? Where is the center of the universe? I think I'll ask Brian to answer. But there's a simple answer, which is certainly wherever I am at that moment. But now, but Brian,
is a correct answer.
As always, Lawrence, you're correct. So, it turns out that if you really want to find a special place in the universe, you're at it. Because every place is effectively the center of the universe. But the center of the universe, because space is not just, this way, and that way, it also has the element of time to it. There is a center of the universe, which is the time of the Big Bang. That's the thing we all share together. And so the universe is expanding, and if you look at a universe that is expanding out in all directions from the time of a Big Bang, everyone in the universe sees exactly the same thing. Where if it's, you're constructed, where you're moving or something, there's no way to get us to being something other than a special place where everyone else in the universe would see something different. And it turns out because the cosmic microwave background is so, smooth and boring, except for those little wiggles at 1 part in 100,000, you sort of know that it's not, we aren't in a special place. We have to be something that everywhere else sees. And so the universe is expanding effectively into the future, as I like to say. You can debate on semantics. But we are at that special place, 13.8 billion years, like every other place in the universe is, from that special point known as the Big Bang.
Okay, and I'll just add by saying that, emphasize that one point, that every observer in every galaxy looks out and sees the same thing. Everything is moving away from them. So they all think they're the center of the universe. Do you want to add into that, or Wendy, or you, as an observer who watches it?
Yeah, well, I mean, but it's not surprising. If you think of it, it doesn't really make sense. If we feel like we're at the center, we look out and galaxies, the more distant galaxies are expanding or moving faster, and so we look like we are the center of the universe. But the point is, any galaxy we were making those observations, we would look out and see that same effect because the universe is expanding uniformly.
It's probably easiest to visualize if you think of a really big balloon that's blowing up. So from any point on the balloon, it looks like everybody else is moving away.
You can try that at home.
Try it at home.
Okay, well, I think we belabored that point enough. Okay. Andy March. Andy? Did he leave? Andy, are you here? Is it Andy? He's shy up there, somewhere way up there. I can't see you, but you're up there. Okay. I think I'll this one for Wendy. When you speak of an expanding universe, are we creating new space or just stretching and thinning out the original space?
Same question.
You can start and we can continue.
It's the balloon again.
I think this is one of those things that's hard to imagine. Where you talk about a Big Bang universe and an expanding universe, it seems as if maybe it's like a bomb and pieces are flying out and we're at the center of that expansion again. And the whole point is that it is space that's expanding. And so the energy density of the universe is the same, but there is new energy. I mean, the overall energy density is the same. So the current picture that we have is something like the cosmological constant, which has an energy density that is constant.
And indeed, space is just getting bigger. And we measure it by galaxies, and the distance between those galaxies increases. And it is one of the. Do you want to say something, Frank?
Just space is cheap. It doesn't cost anything to make.
In fact, it's actually no. In fact, it's actually the opposite of cheap. It's better than cheap, because one of the things if the energy of empty space is non-zero, as Brian has discovered, then the crazy thing is, as the universe expands, it looks like the total amount of energy is getting bigger because the volume of the universe is increasing. But the great thing about this, most of you who took physics in high school knows that gravity sucks, and Brian discovered that it really blows, and what that means, though, the really weird thing is we've discovered that the universe is doing work on space as it expands because of this weird negative pressure. So it's doing work, dumping energy into the universe all the time by the expansion. So it's better than free. It's almost like having.
So aside from the jokes,
okay,
it's kind of, what's really. I was thinking, why physicists are sitting here making jokes about confronting Einstein's theory of relativity with their everyday experience. And so they get used to various principles you're taught in school, like energy is conserved, so if the universe expands, who's putting the energy in, and et cetera, et cetera. And we equally enjoy those conflicts of ways of looking at things and joke about it, even though we actually know that we should learn in high school general relativity, and then none of this would appear mysterious.
Okay, that's a good way.
We all agree on the equations, but how to talk about them in ordinary language can be challenging.
And it's challenging. I mean, I think we should all point that out, especially the theorists, that these ideas aren't just challenging. They're challenging for everyone. They're very confusing and challenging for the people who work on them, and that's what makes it fun.
For the experimentalists, it sounds like a Wall Street bubble.
Yeah. As I often say, if you're a theorist, the most exciting state to be in is either confused or wrong. I don't know if Frank and David, I'm often. Chris, there may be many Chris's out there, but the Chris who asked the question. All right, do you know who you are? Okay, well, Chris, it's about the LHC. Yes? Okay, well, you can, okay, Chris, I'll this one to Maria. Any unexpected results from the LHC?
There have been unexpected results in the low energy regime, which is quantum chromodynamics, and it has to do with counting the tracks of low PT particles. We have been able to, we published that, and it was in fact the first paper that we published from the LHC. Unexpected not in the sense of getting in the realm of new regimes, of new high energy scales, but in terms of what we know for the standard model and the low energy phenomena, we are discovering new aspects of it as we go to higher energies of collisions. Unexpected in terms of higher energies. In other words, if we have new particles, heavy particles, something that would indicate that supersymmetry is there, or that we have a dark matter particle, we have not seen anything. However, you have to remember that we are operating at a little over half of the energy that we were supposed to, because we blew the LHC in 2008, as you remember, and so we recovered very fast, but the very fast had as a consequence that we're not going to go to the 14 TeV, tera electron volts, but we would run at 7 and 8 TeV. Despite that, we did discover the Higgs, of course, which is an impressive feat, if you ask me.
To me, the most unexpected things about the LHC are, First of all, that it works.
Yes.
It's an extraordinary feat of engineering. Secondly, that you can pretty much understand what usually happens there based on the standard model. It works extraordinarily well. And the fact that we can calculate.
The first two things,
But
of course, for experimentalists is a given.
As a theorist,
We built it like that for this, so we're not impressed with ourselves.
Well, there's two things. I would say that the discovery of the Higgs, for me, is the biggest unexpected result. I was sure it wasn't there, first of all.
Yes,
It just seemed
there's
too
many
too
people
simple.
who thought that.
Yeah.
You're not alone on
Yeah.
that. There were people who thought.
I lost 2 first-class air tickets to Australia on that.
Well, I collected quite a bit. I collected quite a bit.
Yeah, you collect a few bets. But you never pay the ones you lose, I've discovered. But anyway,
Look at that.
You can see when the bets were going on. We had it also on eBay. We were selling bets on the Higgs discovery at some point.
but the other thing that's
So we
neat
could
about
make
what you
some
just
bets
said is that what you couldn't have discovered the Higgs if it weren't for having a theory of the strong interaction, because of the trillion particles, trillion events that the one is the Higgs. Almost much of the trillion is due to the strong interaction. And so what's really amazing is one person's Nobel Prize is another person's noise.
Yeah,
Well,
but
David and I have lived through the wonderful, but in some ways humiliating process where people used to talk about testing QCD, and it was an exciting frontier.
Yeah.
Now it's the same thing. It's called calculating backgrounds.
So another way of putting it is which again is certainly the case with QCD, is that from a theoretical point, this year's great discovery is next generation's homework problem.
Absolutely. Absolutely. We all give
Or this year's great discovery, like the Higgs particle, for example, will be next year's background.
Yes.
it is this year's background. We already put all the Higgs processes for this resonance we found at 126. We calculate the rates of this particle going to standard model particles, and then we consider it as background to all the SUSY searches, of course, and any exotic other kind of particle, of course. The Higgs is already a background for us.
to be less facetious for a moment than I normally am, it is really a remarkable facet of science, and David sort of hit on it, that one person, the great discovery today is the homework of tomorrow, and it's really interesting to see that things are very confusing at the time when you're working on it, and science progresses so that when it's reformulated, it seems easy, and we all give the calculation you won the Nobel Prize for as a homework problem for graduate students now. And it's wonderful to see how science progresses that way. The confusion that we're all living in now, 20 years from now, will just seem obvious.
But, there's a great aspect of, of this progress from discovery to homework, which is our students and our students. And today I met a great-great-grandson, intellectually, one of Frank's grandsons here. I really, it's difficult for me to admit, might even understand QCD better than I. So each generation actually understands physics, these basic physics, better than the previous, and teach it better, and that's how scientific progress happens, which is why, it moves down from something studied by, advanced researchers to high school eventually.
Okay, let's move on. Art Evans, are you there? God, no one was as excited as Nadine. I don't know what the problem is.
Out there, right there.
Is there Art? Okay, good. Now, you asked this question for Wendy, but I'm going to ask it to Frank because I have another question for Wendy. But Frank can give the first answer and Wendy can build on it. So but since you brought it up, Frank, why is the observable bending of light from distant galaxies proof of dark matter? And Wendy can add to that, but I thought I'd give you a first crack.
Well, there's a quantitative relationship between the amount of bending, and the amount of matter that's responsible for it, basically because it's the gravity of the matter that's bending the light. And you can look in that direction of the sky to see if there are galaxies and other forms of matter that we know about that are sufficient in their mass to do the bending that we observe. And what's found is, in all cases, it's not, that there's much more bending than can be ascribed to the matter that's visible of ordinary kinds.
You want to elaborate on that a little bit more, Wendy?
Well, I would just add that the progression from first Zwicky's observations of the velocities of galaxies in clusters to Vera Rubin's observations of stars within galaxies to Einstein had predicted the bending of light when we finally were able to get X-ray satellites and measure the hot gas at temperatures of about 100,000 degrees Kelvin. Also, there was a lot more gas there than you could hold in a cluster. It would have evaporated away. And it's just another interesting example. It's very different physics in all of these cases.
Yes.
It's indicating that there is more matter there than we can see in the luminous stuff.
That's right. I mean, people have commonly expressed the possibility that maybe it's not more matter, dark matter, but some modification of gravity or some unknown effect. And it could be, I suppose, but the picture of it as being a new kind of particle, really, explains many, many different facts that would otherwise be coincidental. So it's not just bending of light, but also many other things that are explained consistently within that framework.
Let me add that I think there's a key point here is that there are, and you need in science, a single observation is not believed. Okay, you need to confirm things. The fact that two different groups, for example, in the case of Brian's case, saw this crazy thing was a very important facet. And so there are many, many different ways of measuring dark energy, and they all are dark matter, and they all lead to the same result. And then that implication, physics isn't just a series of facts. They fit together and they make other predictions. And if you take that amount of dark matter, you can make predictions about how galaxies will form. And then you can compare galaxies today to the microwave background, and that comes out. So it's not just a series of unrelated facts. The whole thing has to fit together, and that's what does it. The other thing I wanted to add to what you just said, just in case people wonder, is that, so how do we know that there's more mass than the galaxies? How do we know how much the galaxies weigh? Well, we have to weigh them in different ways. You know, it has to be independent of the ways we're determining dark matter. One of the ways is we measure things we can measure the mass of the Earth by seeing how fast the moon goes around the Earth using gravity. We measure the mass of the sun by seeing how fast the Earth goes around the sun. We measure masses of galaxies by seeing how fast objects on the outside of those galaxies are orbiting around. And that allows us independent ways to measure the mass of galaxies, and then we can look at a big cluster and say, well, we know the mass of all the galaxies, but there's too much bending to be accounted for all that. So there's lots of independent ways of measuring things. Okay, Wendy, how do you, a related question from Anonymous, which one of that would you yeah. How do you know the bending of light from distant galaxies isn't due to undetected massive black holes? And maybe Brian.
So that is something it relates also. So in the 1980s, when people were first wondering about what the dark matter could be, so there was this evidence, and the obvious things were the first things that people looked at. So things, for example, like what if there were planets or rocks? What if there were black holes and they were contributing to the dark matter? And each of these things has observational implications. So if there were dust out there or rocks, or unfinished planets, those would radiate in the infrared. So people looked at the infrared background. If there are black holes out there that we might not be able to see, as matter falls into the black hole, that would emit X-ray radiation. So people went looking for that. It wasn't there. And then people said, well, maybe there are failed stars, things called machos in the halo, for example, in the Milky Way. People went searching for those, did huge surveys, and it turned out they weren't there. You know, these were failed stars that, or even stars that had ended their lifetimes, no longer shone. So one by one, these things were ruled out, and what got left standing was a relic particle from the Big Bang. And now there are searches everywhere, and particle accelerators in underground laboratories looking directly for dark matter, and we'll see where that leads. There's still no experimental verification yet of what the dark matter candidate could be, but people are trying really hard.
Okay, and the bottom line is that black holes are actually quite bright in the sense that they can't hide very easily. Big black holes. Okay, this may be for everyone, or at least maybe the particle physicist, but maybe everyone wants to chime in. What is the most? It's also from Anonymous, who's been asking a lot of questions. What is the most important, impactful piece of evidence missing from modern fundamental physics?
Evidence?
Yes. What are we missing? What piece? What do we need to know? And so that's a difficult question. Anyone want to start?
Well, I mentioned too in my little discussion. I could mention several others.
Just one.
I'll mention one more. Okay. Another very fundamental observation that would start a new field and open up many windows would be observation of what's called proton decay, or the instability of matter, which many of our unified theories, well, all of them basically, predict. And many of our most plausible theories predict are not far from experimental realization. So that would be great, because then you could study how it decays. You would learn enormous amounts about interactions that are otherwise inaccessible, that are very fundamental.
Maria, as an experimentalist, what bit of evidence would you like to see that's missing?
Well, I'm looking for all the sort of evidence that is missing. I'm making experiments for that. But having thought of all the stuff we discussed today that has to do with dark matter and dark energy, it seems to me that the nature of space-time and gravity is where some of the mystery is held. And this is what David elaborated in his talk, the emergent space-time. Once we understand gravity, because dark matter, we know it interacts gravitationally, and because dark energy, we know it has a gravitational connection, then I think maybe the way we think can be formulated.
Yes.
So Maria, as an experimentalist, gave a theoretical answer.
Yes.
And I, as a theorist, will give an experimental. And in agreement with Frank, what we desperately lack are clues which are to phenomena that occur at this incredibly short scale that we can't directly measure. And you guys aren't going to directly measure anytime soon. And one of them is proton decay. There are others. And two of them would be monopoles, magnetic monopoles, or defects of any kind that are often contained in unified theories that put all these forces together. They predict generically point-like particles that carry magnetic charge, not just electric charge. Proton decay are all, we believe, windows into what happens at the unification scale. That would be of immense importance.
Mm-hmm. Okay, I'm going to...
And then, just something which nobody's mentioned here, neutrinos, properties of neutrinos, which indicate a sort of intermediate but inaccessible scale of physics at the moment.
Well, and it's a probe. I think it's a probe. This for neutrinos. I'm sorry, I will jump in on this,
okay.
But it is a probe to high energy as well, as we know. But also for neutrinos, an amazing, I think, fact is that everything we predicted for neutrinos was proven by experiment to be wrong, and so those little ones are. we need to look at them better.
Okay, I'm gonna cut this off. I'm gonna pretend I'm John McLaughlin. I'm gonna say wrong.
Wrong.
For those who watch that program. I think the most important piece of evidence missing from modern fundamental physics is a piece of evidence that we have no idea of right now, a piece of evidence that will in fact change the way we think.
Yes.
Not one we anticipate.
We're all waiting.
But one that we don't anticipate at all.
What is the name of this evidence? Or it
That's
doesn't
the
have a name?
answer. No more discussion. I know we have two more questions, and we've got a little time, and I'd like to get to both of them. One sort of question was asked by two people, more or less, and I'll read both. But one of them was anonymous. The other is Andrew Shabala. Andrew? They both involve multiverses.
All right.
And so we've gone from the sublime to the ridiculous, as some people might say. But what evidence, this is a very important question, what evidence currently exists to support the existence of multiple universes? And a similar question, how can you test the multiverse if you can't see these other universes, since they are always beyond your Hubble horizon? A very similar question. So what evidence is there of a multiverse? And I'll begin with Frank.
Well,
because I know that David will want to say something.
Well, as in many cases,
After that question.
our theories that we can test in certain respects, we may not be able to test in others. So if we had a really compelling theory that among its consequences predicted that there are far, far away regions of the universe that are multiverse, that have essentially different physical laws than we observe in our accessible part of the universe, then we would start to believe it. In the particular case of axions, the theory itself predicts that on very large scales, the amount of dark matter in the form of axions varies. And in most of the multiverse would be much larger than is allowed here, than we see observationally here. So if we see axions with the appropriate properties in other respects, and the theory tells us that we have to live in a region that's unusual, where the density of axions is small, it would be compelling evidence that the things are very different elsewhere.
David?
But that's an example.
Okay.
You mean, if the question is there any evidence for the so-called multiverse?
For multiple universes.
The answer is very simple, no.
No.
Absolutely. Yeah, the answer is there is no evidence, but there are reasons to think there might be. So there is, that's really important. There's no evidence for extra universes, just as there isn't the slightest bit of evidence that there are extra dimensions. But there are good theoretical reasons for people to think of these possibilities. I'll add one thing. And
That's not what I meant by my no.
Oh, that's okay. Good. But let me just say there is a way. You might think it's metaphysics, and it's really important to realize that theorists aren't doing metaphysics. And Frank alluded to it. But the point is, there may be many universes that we can never see and never detect directly. You might say, well, that's just metaphysics. Or worse, religion. But anyway, the point is, if you had we knew atoms existed long before we could measure them, because there were a lot of other predictions that you could verify. So if we really did have a grand unified theory that explained the ratio of the proton mass to the electron mass, and if we had a theory that explained why there are 4 forces in nature, and there were 50 different things it predicted, and one of the predictions was that there had to be other universes. Yes. That would be not metaphysics. We'd say, look, it walks like a duck, quacks like a duck. Yes.
Yeah. So I really don't want to get into this, but one aspect of this, which is the one that I find most uncomfortable, aside from the fact that it really is a word you haven't, or no one here has actually mentioned yet, the anthropic principle. So the whole attempt to make use of this notion tends to lead most people who work in that direction to anthropic arguments. Now, unfortunately, one can't prove, and if one could, the argument would end that this is logically inconsistent, unfortunately, yet. But there's something that most physicists feel, especially given the history of physics, very uncomfortable about in this set of ideas, which is independent of the anthropic principle, and that is discussing a framework in which one discusses things that are, in principle, never observable. And that is true of a vast collection of causally disconnected so-called universes. So we all feel uncomfortable with that, and we would all be greatly reassured if those who follow that direction, and some have tried, not successfully yet, to reframe this in a way that doesn't use as a conceptual framework, in principle, unobservable things.
Okay.
It smells of angels.
Okay, excellent. Now, that leads to the last question, which is also from Anonymous, who I applaud for the quality of your questions, whoever you are. And I want everyone to answer this one, because I think it's a good way to end. And you can answer it, you can take it to mean many different things, but I hope you'll... Anyway, if we gain evidence to prove the existence of parallel realities, and you can take by that whatever you mean, how would it benefit our society? And I think it's a good way to end. Of course, I'll have the last word. So, Maria, why don't we start going down? I think it gives you time to think, David.
Really? you throw this to me? No. I think all the data we have, we interpret for the physical world reality that we have around us, and that's one universe, the universe. If there are pockets of the universe or other universes that people are talking about, we eventually, something will happen to show us this. But parallel realities we can have on our brain, and we can think of them, and it can help society a lot if people fight in parallel universes and not in the same one. And we can take it to the DOE and say that in the parallel universe, those competitors are taking more money so that we can build our collider here. So this kind of thing, you can... no.
Thank you. Okay, Frank?
Well... There are parallel universes. There are lots of them.
All right.
You and for instance, if you own a dog, the dog lives in an entirely different sensory universe than you do. The dog has very poor vision, very excellent smell. It really, in a very real sense, lives in a different world.
Okay, the question isn't are there parallel universes. The question is how would it benefit society?
Well, you should respect your dog. Because
That's probably very useful advice.
I was going to relate it to physics a little bit. The cosmological multiverse is one parallel reality, but another parallel reality that's very important and is really a frontier of engineering is the world of quantum mechanics. Yeah. And there are debates about what exactly the quantum world is. One leading interpretation is called the many worlds interpretation. Other interpretations are more conservative, but every interpretation is radical in some ways. And a great frontier, not just of abstract science, but of engineering in the 21st century, I feel sure, is going to be really coming to grips and exploiting the possibilities of the vast universe, multiverse, opened up by quantum mechanics.
Excellent.
Okay, so
I'm going to applaud everybody.
Short answer to the question
Yes.
is I don't know. And I would add to that, I think we need to be patient. And I think the history of science has shown that there clearly are things we don't know. There are ideas that will come about in the future, and there's technology that we can't now predict. And I think a good example is general relativity. And the global positioning satellites we use now need corrections for both special and general relativity. So Einstein, sitting in his office over a century ago, was not imagining any practical application, how this would help society. But eventually, even these things that seem untestable, if the theories are describing something about the world we live in, there will be something we're not thinking about now that is going to connect to what we're thinking about. So I don't know, but I would not be surprised if there is something.
That's a great example. It worked out once, I think, in a minute and a half without general relativity, you wouldn't be able to navigate your way using GPS. Good. I like that one. I'm going to applaud that one.
So, Lawrence, after hanging out with you for extended periods of time over the last few years, I do realize there are parallel.
Perpendicular.
That aside, I was going to give an answer pretty similar to Wendy, but I'll expand it and say that when you get knowledge in any form, that knowledge is of use, I think, for humanity, because humans, at least what I have found traveling the world, universally want to understand their place in the world. They want to understand, how things work as deeply as possible. And that knowledge may be the thing that inspires someone to invent a new toaster later on because they got interested in science. It may lead to some new technology. It may not. It may just be about realizing who we are and what we do. And that's part of a condition of being human. So I, like Wendy, can't tell you exactly what it would do, but it's not bad. It's good, and it's worthwhile knowing.
Wisdom, David.
So some of my colleagues have copped out by...
I was feeling lonely.
Okay.
By arguing forcefully and beautifully that all knowledge, scientific knowledge, even as remote as it might seem from everyday life, in the end will and has contributed to the benefit of humanity, which is absolutely true, from quantum mechanics even to QCD and particle physics. Eventually will, I have no doubt. But parallel universes, as far as I can see, so far have only benefited Brian Greene.
Excellent. Okay, I'll applaud that. Okay, well, this gives me a chance to answer. The real answer to that question is all of you. People seem to think that these vital questions and esoteric questions about the nature of reality are of no interest. But they are of driving interest. 2,000 people will come to listen. Every time we're on the radio or TV, people are fascinated. People don't understand that I think these questions are fascinating to everyone beyond scientists. So you are proof that being human, these questions are interesting, pleasant. The aha experience of learning about nature is orgasmic. And I hope that we will continue to bring you in. And
feel it coming.
Well, someone said it for me. But the point is that
Are you going to play Sally?
that these ultimate questions are of interest, and that's why we continue to do what we do here. I look forward to welcoming all of you back in April as we continue our exploration of our origins. And I want to thank you very much for coming tonight, and I want to thank this wonderful